Hi guys, I'm Andrew. I'm one of the TAs for the lab course that you're taking this summer. What we're going to be talking about today is the content for Lab 4, motion in 2 dimensions. So the things that we're going to try and discuss in today's lab is that we want to learn how to subtract two vectors and identify their change in velocity, their delta v. So what is delta v? Delta v is defined as the final velocity, otherwise vf, minus your initial velocity, vi. So we'll get into what that actually means a little bit later. Another thing that we're trying to identify today is the direction of the acceleration based on delta v. So if we're looking at delta v, we have a couple of vectors that we subtract from each other, and then the resultant of that will then tell us the direction of delta v. The nice thing about delta v is that tells us the direction of A, of our acceleration. Delta v is in the same direction as our acceleration. The other thing that we're trying to cover is we're going to learn how to use time exposure graphs. Time exposure graphs are sometimes they're a bit difficult for people to understand, so I'm going to try and break it down as simply as we can. So with that, I'm going to bring out a binder here. The binder has a nice little slope to it. If we look at it right here, it's got a nice slope. And what that does for us then is it allows us to, if we have a ball and we roll it, you see how it moves, right? It has what's called parabolic motion. That's kind of something that you would see if you were to throw a ball straight up into the air and it comes back down. So what I'm going to do then is I'm going to try and create a fake time exposure graph just by doing this and tracing out the path of the ball, right? So for a time exposure graph, the concept behind it is that at some point in time, the ball has moved some distance, and then at another point in time, it's moved some other distance, and that ends up looking like something close to this, where the ball starts moving quite quickly at first. It goes up, starts to slow down a little bit so that this time exposure is not as long. And then you come up to the top, it's really short, and then as it comes back down, it starts to gain its velocity back, and they end up being nearly the same length at each of these different spots. So what does that tell us? That means us that in some time interval, the ball went from here to here, and in that same amount of time, the ball then went from here to here, and then from here to here, here to here, here to here, and so on. So if we're trying to express these as vectors, then if we're trying to make them displacement vectors, and that's what this is, it traveled from here to here, that's just a delta x, otherwise you might call it d. That's just displacement, it's just some distance traveled. Now how we relate that then to our velocity, because we're actually interested in v final minus v initial, right? Well, displacement is just velocity times time, right? So we can write v equals delta x over delta t, where delta t is just whatever time interval it was that this camera was taking pictures at. Well then we can actually just relate this directly to our velocity then, right? Because if this is our displacement here, I'm going to go ahead and draw this in red. Our displacement, it goes from here to here in that direction, and that one is going to be the first displacement. Otherwise, we can simply just say that that is our velocity initial. Okay, so I'm going to color this one in purple. It might be a little bit difficult to make out the differences between them, but the next one is going to go from here to there, and then this right here, that one is our velocity final, or a representation of our velocity final. So what I'm going to do then with these two, it's kind of hard to see because this bled through, but that's all right. I'll just use the black for now for this one. We're going to shift these because the rule with vectors is you can move them. That's fine. You just have to keep the direction right. So we do our best job to kind of keep this parallel. So we'll go ahead and say right here to right here. That keeps our direction the same length. And if I can grab a ruler, perhaps, I can then measure this out and make sure that we have the same length. Okay, so that's about 2 inches, so we'll draw a line that's 2 inches in the same direction. There we go. This was our V final. Okay, and then here's our V initial. We want to try and keep that same direction, right? And this one is about 2.5 inches long. If you want to see it from the 0 point, about 2.5 inches long. And then that one was about that angle there, right? So this is our V initial. Okay. Now, I'm going to move this out of the way. The way that we find our delta V, our change in velocity then, is simple enough. We just take our velocity final minus our velocity initial. Now, we learned in previous labs that the opposite of a vector, the negative of a vector, is just 180 degrees flipped. So that will tell us the direction of velocity initial when we're trying to subtract it from the final velocity. But the way that we want to start off this problem then, the change in velocity equals your velocity final. So let's go ahead and draw that first. And we can just trace it out now because it's right through there. There's our velocity final. Then we want to then subtract velocity initial. Well, velocity initial is just the opposite direction of the initial velocity. So instead of having the arrow pointing this way, we can actually demonstrate negative velocity. So a negative velocity then is simply just this guy right here. So if we then subtract this line from our velocity initial, we just go ahead and draw it out using the tip to tail method. And there we go. That is our negative velocity. So the question is then, which one of these two lines is our change in velocity? Is it from this way to here, starting at where we started and pointing to where we finished, or is it where we finished to where we started? Well, in a situation where we have a resultant, we actually go from where we start to where we finish. So let's go ahead and do that in red. That is going to be this direction here. That is your change in velocity. Okay. So that's a simple enough thing to see. As we go up around this corner here, then our change in velocity at this point is going to be down and to the right. And that was our delta V for this situation where this was our V final and this is our V initial. And that makes sense because in order for you to have some kind of acceleration that tilted you down towards the bottom of the paper, you needed that exact kind of direction that you're looking for in the change in velocity. Now, one of the things that we wanted to do was determine the direction of acceleration based on our change in velocity. But we also stated that the change in velocity is going to be the same direction as our acceleration, and that's exactly what we see. We have a change in velocity that points downwards pretty much, and that's what we expect. So let's just go ahead and rewrite that again to reiterate. Our change in velocity is defined to have the same direction as our acceleration. I'm going to throw in direction there because that's what the point is, the same direction as acceleration. Now that we've done that, we can actually explore a little bit more complicated systems. And what we're going to do then for the lab is we're going to have some time exposure graphs that we make, and they'll end up looking something a little bit like this. So I'm going to draw this out a little bit darker so you can make out the lines. So they're a bit too close right here. Can't really make them out, so let's just ignore all these parts from here on out. So then let's go ahead and say here's a line here, and we're assuming it's going downhill. There's a line here, line here. As you see, as this goes down, this is basically a drawing for a ball that rolls down a hill. As the ball rolls down the hill, it starts to pick up speed, and that's why the length of these lines get longer and longer. And then as it goes back up, you start to notice that the lines get shorter and shorter. And that's because it's losing its energy, which then lowers its speed. And as you get up to the top of this hill, you get really short, and then they go back down. So if we wanted to express the velocity, or the change in velocity of the graph between 2 points, let's say point A here, point A, we can then take the two velocity vectors adjacent to it. So we got velocity initial here, that's the one that was before, and here's the velocity final, the one that's after. So this one, they look very similar, so we're going to have a very small change in velocity. So we're going to go ahead and draw velocity final. Let's go ahead and look at that. That one is, we'll do this in centimeters because it's a lot smaller now. So that one is about 1.7 centimeters long, and we'll try to make sure that we retain the direction of that. 1.7. Okay, that was velocity final. And if we remember correctly, that delta V is V final minus V initial. So then we have to take the opposite of V initial here, which it looks like it is 1.6 centimeters. So this is going to be a very difficult line to draw, and I would almost argue that it's in the same direction. So if you're dealing with a problem where you have two lines that overlap, my best suggestion for you is then to draw the line not on top of it, but just below it, so that you can distinguish the two. So I'm going to go ahead and draw a line that starts right where this guy finishes and maintain the angle here, and I'll just draw it 1.6 centimeters in that same direction, right? Now, if we're doing it this way, we have to be careful because now we have this distance that we have to make sure that we're not forgetting, right? So basically here, we're drawing a line from where we start to where we finish, and if we were to scooch this negative V initial line up over that, right, we're moving it that way. So then basically we would see that we start with V final, go here, starting from V, the end of V final. We then go back over to the left, and then V initial ends up getting us right here. Now, when we were dealing with this problem before, when we were subtracting V final for V initial over this hill part right here, it was a lot easier to see where we started and where we finished, right? Well, we started at this point right here, and we finished right here. So the change in velocity is just this tiny little bit right here from where we started to where we ended up. So delta V, it's kind of tiny. So delta V right here is just this really small acceleration downwards. And that makes sense because, well, we started from initial velocity, we rolled downhill a little bit more. As you know, when you're rolling down a hill, you speed up. So this makes a little bit of sense that we would have some small acceleration down the hill. Okay, now, with that being said, you've pretty much been equipped for the entire lab, but let's look at just one more picture that we might encounter in the lab, and that is going to be something like this. This is just a ball that's swinging on a string, and as it gets closer to the sides, you'll see that the velocities are longer, and as it gets to the perpendicular sides here, the velocity gets shorter. So you would imagine this swings fast, 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 slows down, and then gets faster, 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 slows down. And this is the kind of graph that you'll be looking at in your lab today. So in summary, we just want to go back over it. Lab 4 is motion in 2 dimensions. We want to learn how to subtract two vectors, use the change in velocity to determine the direction of acceleration. Well, we know now that the direction of acceleration is the same as a change in velocity, and we're doing this through time exposure graphs. We're learning how to do all this using these time exposure graphs. And I believe that's all we need to talk about today, so thank you very much.